This video discusses the Endo rule. In the Diels-Alder reaction, we can have the dienophile, which is shown in green, react with the diene in different ways. We can have the dienophile approach the diene from the top or from the bottom, and usually this will result in the formation of stereoisomers. Another possibility is if we consider the orientation of this R group that's on the dienophile. In this case, we can say that the dienophile can have an exo approach or an endo approach. In the exo approach, this R group is away from the diene. In the endo approach, the R group is going to be directly below the diene. Now let's look at the exo transition state and product. Remember that the exo approach is when the R group is away from the diene. The way we've drawn the diene with this carbon pointing up is just to show that as this dienophile comes in from the bottom, it's going to push this carbon up. If we draw arrows, we know that the diene is going to attack this alkene. This is in turn going to attack carbon number 4 here, and we're going to form a new pi bond there. In the transition state, we are going to show any bonds that are being formed or broken as dotted bonds. And so this is the new pi bond that's being formed. These are the 2 new sigma bonds being formed in red. And these are the 3 pi bonds that are being broken. And we get all of that just from the arrows that we drew. At this point, it's important to put in this hydrogen so that we know the stereochemistry in the final product. When I draw the final product, I'm going to first just draw it exactly as it is here, with the new bonds being made and the bonds that are being broken. So I've got this cyclopentadiene, I've got a new pi bond that I've made, and I've got that from this arrow here. I've broken these 2 pi bonds, so that's alright. I've got sigma bonds here. And then to our dienophile, I've made these 2 bonds, so I know that there are 2 new bonds here. And then I've got this sigma bond here. Remember that we've broken this pi bond, so now we just have a sigma bond. To this carbon is attached the aldehyde. Okay, so this carbon has the aldehyde. We put in the aldehyde, and we're going to look at where our hydrogen is. Our hydrogen is on this side, and so we're going to show our hydrogen on this side. Okay, now this is a 3D depiction, so we're showing it in a 3D depiction, not a flat cyclohexene form. So in this case, if we were to redraw it, we can draw it as a bicyclic system. So it's got a bridge that's going up. This is the double bond. Our hydrogen is going straight down. So our hydrogen is closer to the diene here. And our aldehyde is going out. If we were to flatten it, so now imagine that I'm going to take this and rotate it until this is in the plane. So I'm going to have the cyclohexene in the plane. So this is the same as this cyclohexene. Here's my double bond. So I'm going to put that in here. Here's the bridge, and it's coming out, which means that you have to show it with wedges. And then on this carbon here, which is the same as this carbon, I've got the hydrogen going at the back, the aldehyde coming out at the top. So the hydrogen is going at the back, and the aldehyde is coming out at the top, and I'm going to show that with a wedge bond here. So you can see that in the exo product, so this is the exo product, because we had the R group come in away from the diene, and this hydrogen was towards the diene, you can see that the hydrogen is towards the remaining part of the diene, and this aldehyde is still outside. So the aldehyde is closer to the smaller bridge here, and the hydrogen is closer to the larger bridge that used to contain the diene. That's how we define the exo product. So overall, we started with cyclopentadiene and the dienophile. We're depicting an exo approach. We showed the transition state, and we made the final product. When we redraw the product, you can draw it either as a 3D depiction, or you can show it with the cyclohexene in the plane, and then show everything else with wedges and hashes. Now let's try this with the Endo approach. In the Endo approach, remember that this R group is going to come in directly underneath the diene. Now if you have more than one R group, you're looking for the electron withdrawing group. Okay, so you're looking for the electron withdrawing group to be underneath the diene. And again, we can draw our transition state. So we're making these two sigma bonds, we're making this new pi bond, we're breaking these three pi bonds. If I were to draw arrows, remember that I start here, attack this alkene, and then go around in a circle. Our product can be drawn directly from the transition state, so we can start with this cyclopentadiene. We've made a new pi bond here. Remember, I get that from this arrow, and then these two arrows show the formation of two new sigma bonds. So I've got these two sigma bonds. And here, remember that the hydrogen is on this side. So the hydrogen is on the side closer to the smaller bridge here. So the hydrogen is going to be up here, which is closer to this smaller bridge. And the aldehyde is going to be on this side here, which is underneath this entire ring. Okay, so if I were to redraw that, I can show the 3D depiction form, which has the alkene there, hydrogen coming out, and you've got the aldehyde going underneath. And this is the same as if I flatten it and draw the cyclohexene here. I've got the bridge coming out, so I'm going to show that with wedges. The hydrogen is coming out of the page, so I'm going to show that with a wedge. And the aldehyde is going at the back. And this is the endo product. Overall, if we start with cyclopentadiene and a dienophile, we can show that the Endo approach, where this electron withdrawing group is coming underneath the diene, can go through the Endo transition state and end up in the final product, where the aldehyde, or the R group, is going to be towards this bridge here. Okay, so in the 3D depiction form, you would draw it this way, and that is the same as this form where you flatten the cyclohexene and you're showing everything else with wedges and hashes. Just like we analyze cyclohexane chair conformations with stability, we can also look at these bicyclic compounds and look at which one is more stable. The more stable one is the thermodynamic product. So if we analyze both the exo and the endo, we can see that there's going to be steric hindrance here because you've got the larger group in the pseudo-axial position, so it's towards the larger bridge. And here you've got the larger group in the pseudo-equatorial position, so it's away, going outside, and it's closer to the smaller bridge. So because you have sterics here, the exo product is the thermodynamic product. So this is more stable, and the endo product is the kinetic product, and that's formed faster. Now let's look at why the endo product forms faster. Now generally in a Diels-Alder reaction, the endo product is favored over the exo, and this is called the endo rule. So even though this is the thermodynamic product, and remember that this was the kinetic product, this is the product that's favored, usually in most cases. The reason that it's favored and formed faster is because of a stabilizing effect of this electron withdrawing group. So now in the formation of this transition state, when you're breaking and making these bonds, this electron withdrawing group has its p orbitals aligned here, and remember that this is a filled p orbital, and it can donate into this transition state and stabilize the transition state with secondary orbital overlap. In an exo transition state, remember that the electron withdrawing group is angled away from the diene, so it cannot participate in secondary orbital overlap. Now pause the video and predict the major reaction product before moving forward. The first thing to do is identify the diene and dienophile. So this right here is my diene, so that's going to be the nucleophile. This is the dienophile and the alkene that's going to react in the dienophile. The best thing to do is to redraw it so that you can see how the dienophile is approaching. And so if I draw the diene, and I can draw the dienophile come in from the top or the bottom. If I choose to show it from the bottom, I'm going to draw the endo version because I know endo is favored. So endo is going to be the major product, and so I'm going to draw the endo version where this R group is underneath the diene. I know that the bonds I'm going to form are here and here. So if I were to draw the arrows, this is attacking here, this is going back up to the diene, and that's where the new pi bond is being formed. So my product is going to have this oxygen pushed to the top because this is coming from the bottom. So the oxygen is pushed onto the top. I've got the remaining of the diene here. I formed a new pi bond here, so that's here. And then here it might help to put in the hydrogens. Now these hydrogens are closer to this oxygen, so when I draw my six-membered ring here, the hydrogens are closer to the oxygen, and then the rest of the ring is closer to the remaining part of the diene. So the rest of the ring is going to be here, and that's going straight down. And that's the molecule. So I drew the carbonyl coming off of the front carbon. So the carbonyl was aligned so that it comes off the front carbon. Now what if I had drawn this dienophile the opposite way? So if I had approached still from the bottom, but if I had drawn the dienophile this way, still an endo product, because this R group is underneath the diene, I would have ended up with, again, oxygen going on the top, and then this is the new six-membered ring that's been formed, hydrogens going out, again, still the endo product, but now the carbonyl is on the back, and that's my product. Now look at the relationship between these two products. They're not identical, but they are enantiomers. Okay, so overall, it can approach from the bottom, and I would get stereoisomers. Again, if you approach from the top, again, you would end up just with stereoisomers. Practice drawing all of them and see if you can identify which ones are enantiomers and which ones are diastereomers. So the final products are here and here. In this particular example, even if you draw approaches from the top, you would end up with these two enantiomers. So the final products are just these two enantiomers. Now if you have substituents on this diene or this dienophile, you do have to try drawing the top-bottom approach and align it differently so that you can get all possible products.